All right, in problem 72, it's very unique because we have a disk. Here's our disk right here. All right, and the center mass of the disk is here, but we don't want to rotate it about the center of mass. We want to rotate about a point on the edge. So essentially we're going to hook an axle out here, and so the whole thing is going to spin around it. So it's kind of like a pendulum going around like this, where there's a rod with a wheel on it and the whole wheel is going to spin down here. And what you're going to do is you're actually going to start it from a zero position here, and you're just going to let gravity rotate it. This is a horizontal axis. And we know that the radius is 0.30 meters and that the mass of this is equal to 5 kilograms. So I'm going to look at it, this is trying to be 3D. I'm not going to do 3D on it. So this is what we got it going here. This is the rotation point right here. When you let this go, the center of mass of this is going to spin around like this. So when it's at the bottom, it's going to look like this. When it's going to go over here, and it would just rotate back and forth as you hang it on the disc. So as it spins, it's going to rotate around a point, but it's going to rotate at a point not at the center of mass. All right, that should be our first clue. We're going to need to know I. But remember, it's not rotating around the center of mass, so we have to use the parallel axis theorem, which is the I center of mass plus the mass times the distance you moved it squared. Well, in our case, it's a disk, so this is 1/2 mr squared. And the distance you're moving this is r. You're moving it to the outside, so this becomes mr squared. And so when you add that together, you get I is equal to 3/2 mr squared. All right. Now, to do this, this is like a pendulum. And a pendulum problem, the easiest way to solve it is to use energy. So we're going to use energy initial is equal to energy final. And you're just going to have it hanging there. You're going to just let go. And so the initial energy is just gravitational potential. But once it goes, we want to know how fast it's going when it reaches the bottom here. It all becomes rotational energy, which is 1/2 I omega squared. Okay? So the thing is going to be rotating around this axis, so the gravitational potential is converted to rotational energy. And we want to solve this for omega. But we're going to expand it a little bit first. We know this is 1/2 times I, but I is 3/2 mr squared. I got that from over here, times omega squared. Now we can divide by m. This is the same m, the same mass of that. And this becomes GH, but 1/2 of 3/2 becomes 3/4 r squared omega squared. Now solving for omega squared, this becomes 4 GH over 3 r squared. All right, but what is h? We didn't have h anywhere. But if you look, when we started here, right, it goes from, and we got to go from the center of mass. The center of mass is here. When it rotates over here, this is where the disk is going to rotate to. It's going to spin to this point here. So the height change is that much. It goes from there to there. Well, that's exactly equal to the radius. So omega squared is just going to be equal to 4gr over 3r squared. But notice that that cancels with that. And we get omega is equal to the square root of 4g over 3r. And we can plug in the numbers for that. It's 4 times 9.8 times 3 times the radius, and our radius is 0.3 meters. We get omega is equal to 6.6 radians per second. Okay. And now, what we want to know actually, there's two parts to this, and I solved part B first. So the questions were, I didn't look up the questions properly, I just went and solved it. But what it really was asking for, number 72, was it says, what is the cylinder's initial angular acceleration? And what is the cylinder's angular velocity when it's directly below the axis? So I just solved part B right here. This is the velocity below the axis. what we want to figure out in part A is right when it starts, what's its acceleration? And remember, it's going to be net torque is equal to I alpha. Okay? Or we can say that alpha is equal to the net torque over I. Well, what's the net torque? Well, you're going to remember when it's up here, so I'm going to redraw it here, it's rotating here. The only thing pulling on is gravity, which is mg right here. But torque has to have a radius vector. This is the radius vector. So the net torque over I is going to be equal to mg times r times the sine of the angle. But in this case, the sine of the angle is 90 degrees, which just becomes 1. And then I is 1/2 mr squared. So you can cancel some stuff out here. The m's go away, right? That r goes with that one right there. That becomes 1. And what you're left with is 2g. Oh, and I'm sorry, this is 3/2 mr squared. I don't know why I put 1/2. 3/2 from up here. So this becomes 2g over 3r. And when you plug that in, you get 2 times 9.8 over 3 times 0.3. And you get that this is all equal to alpha. Alpha is equal to 21.8 radians per second squared, or 22 radians per second squared. All right, that's part A. So I did that kind of backwards. This is part A, this is part B. Notice though, look at this closely, this is A, alpha, when it's up here. But as it starts to rotate, if this is the rotation point, a little bit later, gravity is now going to go down this way. This is the radius vector. There's going to be an angle that's not going to be sine of 90 again. So if you were trying to figure out what the alpha is changing continuously as it rotates. Just like in a pendulum, the component that's making it move changes. And so the easiest way to do this is to do it as an energy problem. That's it for number 72.